So let's try to understand what the integral calculus is all about. Imagine that you have a function. The historical development of integral calculus was quite obvious, because human beings always try to understand, like if they want to go from point A to point B, they want to understand what is the way to go from point A B to point A. So initially that point A, it was fx. So Newton, Leibniz, all these stalwarts in mathematics, they discovered that they wanted to understand the rate of change and the slope of the function at a certain point, the line approximation, and they discovered the derivative. Okay, let's say d by, let's call it a function d by dx. If it's an operation. Okay, if you operate it on this fx, you go to f dash of x. Now it's natural, like if you go from place A to place B, and you want to come back to place A, right? I mean, that's what human beings want, right? Like naturally, even if you travel. So they also wanted to understand how to come back from f dash to f. Like, what the properties are. Like, there must be an operation, right? What operation do we need? So this was the fundamental question human beings asked. So the asking is the inverse operation of the opposite, or in the inverse operation of differentiation. This was a starting point. But there were troubles. What kind of troubles? There were serious mathematical troubles. So what kind of troubles? The issue was that, understand this very carefully. The issue was the following, that, remember Darboux theorem? So what does Darboux theorem say? Darboux theorem says that if you have a function fx, uske f dash x also follow f is differentiable. Uska f dash x also follow the intimate value property, IVP. Okay. So f dash x has certain, a sense of, it's like it's not a normal function. Not every function can be derivative. So it's like it's telling you not every function can be a derivative. Okay. Do you understand this point? Not every function can be derivative, because not every function follows this property that it always follow IVP, right? So the question is that, what are those functions which can follow derivative? Let's take an example. I'm like, that's the question I'm coming to. Okay, so when I tell not every function can be derivative, it means that not every function can follow IVP, right? Not every function can follow IVP, the integral property, right? What functions? Which functions? Give me an example. Box function. You're right. Box function is an example. So if you take a very boiled down, easier, watered down function of box function, similar, you can take this, that fx is like this. It's a sine function, sine of x. That means it's 1 if x is greater than 0. It's 0 if x is equal to 0. And it's minus 1 if x is less than 0. So observe, if you take the individual in the region, let's say -1 to -2 to 2 in this region. Okay. it's already x. If you take in this minus 2 to 2, it takes both the values minus 1, 1 and 0, right? But it doesn't take other values, right, in between. So it does not follow IVP. The question is that, so what we are trying? We are trying to get back f from fx, right? So the question is that, since we're trying to get back f dash x, like fx from f dash x, the question is that, can't we, like that's what we mean, that operation, that is what we define as integration, okay? The question is that, therefore, cannot we integrate gx, this sine of x, because from f dash x, we're trying to get back fx, right? From f dash x, we are trying to get back fx, right? So we are trying to do integration of f dash x to fx. Even if you forget that f dash x, can we say, cannot we integrate this? Cannot we integrate minus this sine function?